Hey, Pete, are you hearing any background noise at all?
I am getting a bit of background noise. Yeah, if you could mute yourself.
All right. I've got spray foamers here that I scheduled like 4 months ago. So,
Shame on
Got
us for rescheduling the conference.
Well, you need that insulation before winter.
yeah, well, it's a pretty big job too. They've been going 2 days and they still got another day.
My goodness.
Well, we are at 1 o'clock, so why don't we go ahead and get started? Welcome everyone to session, what are we in? Session number 12, LiDAR. We've got 2 talks for you this afternoon. Should take us to 2 o'clock. Each talk is going to be about half an hour in length, including Q&A and some transition. So hopefully you are all in the right place. Again, session 12, LiDAR. So our first talk, I'm sorry, a couple other notes quickly. If you have questions, please place those in the Q&A section rather than the chat, and we will take questions at the end of each talk. We should have at least 2 or 3 minutes, hopefully a little more, for questions from both presenters. And with that, I'd like to introduce Adam Derringer, Senior Project Manager from Ayres Associate, and the first talk, Mapping Your Environment with LiDAR. And take it away, Adam. Thank you.
Thank you, Pete. Go ahead and share my screen. So as Pete said, I'm a Senior Project Manager at Ayres Associates. As a longtime GIS manager, spent about 13 years managing a GIS department before I came over to Ayres in order to play with big data. So I find that analyzing this data is a lot of fun, but really part of my job is running big ortho imagery and LiDAR programs. And I found very early on that people would get access to LiDAR data and then never know what to do with it. So that's pretty much what we're going to focus on in my discussion here today. I am more of a techno guy, not much of a BD presentation guy. So please ask questions. That's the kind of stuff that I enjoy. I want you guys to walk out of here with some ideas of what you'll be able to do with LiDAR data. So just a little bit of background information for those of you that are just getting into LiDAR data is there's a whole lot of new LiDAR data coming into Minnesota. I'll briefly cover that. I want to talk about why it's important, where it's available, what can you do with it, some historical challenges, and then hopefully we'll have enough time in order to actually show you some LiDAR data in action. So my company tells me I have to talk about my company. So Ayres Associates is a architectural and engineering firm, but actually the largest division in the company is geospatial. So that's kind of what we call our aerial mapping team. That's our big data team doing aerial imagery, LiDAR, data processing, GIS, and then we've got a full traditional survey teams as well. What is LiDAR? LiDAR stands for light detection and ranging. It works very much like sonar, where sonar sends a sound pulse from a boat and that hits the bottom of the ocean and returns back. We know how fast sound travels, so we get a measurement of how deep the ocean is at that point. LiDAR in an airborne sense works very similarly. We'll have a plane with a LiDAR system on it. It shoots a pulse of light. We know how fast that light is traveling. So it shoots out of the plane, it hits certain things, and then it returns back to the plane. Again, knowing how long that takes and the speed of light, we can then get an XYZ point. When you get millions and billions of these points, we can get these really high resolution surfaces. And as software gets better and better and better, we can identify objects better and better for feature extraction. So everybody used to do these projects on their own, or there'd be a federal project, but a program called 3DEP came along. Some of you are going to be familiar with this, as Minnesota has gotten involved in the 3DEP programs. 3DEP stands for the 3D Elevation Program. It's primarily run from the USGS. The general idea is they want to get new high-grade elevation data across the entire United States on an 8-year cycle. I'll stop there and say that's not likely to happen. There's just not enough money in the program or in communities to be able to collect LiDAR data every 8 years at this point. But that's the general intent of it. all that data needs to meet certain quality level standards. These were set in about 2014 for quality level 0, 1, 2, 3, etc. That the data needs to meet in order to go into the federal program. And if it does, you can get these cooperative grants. So you're going to be partnering with federal agencies, state agencies, and local agencies, all working together to collect data one time to meet this national standard, so all data works together. What are the benefits of having this LiDAR data? Well, the primary government use of the data has been flood risk management, and it remains flood risk management. Also, as data is getting better and better with higher standards being achieved, we start to get into infrastructure management, construction management, natural resources and conservation, looking at riparian areas. Agriculture is using this data more and more for water runoff studies. You're getting into precision farming, water quality and supply. I deal a lot with territories that have sinkholes and trying to utilize the data to identify where those might be. So if we're going to spread manure on the side of a hill, where's that going to go? Is there a sinkhole nearby? LiDAR data pays off on about a $1 to $5 ratio. So I put $1 into LiDAR. If everybody's using it the way they should, we should pull about $5 out of that LiDAR project that we'd get in return. So history of LiDAR in Minnesota. Minnesota was an early adopter of trying to get statewide LiDAR information for all the different purposes that LiDAR can provide. Again, starting with water quality and drainage studies. This is a map that you can find in Minnesota's LiDAR reports. LiDAR was collected about 2007 to 2012, and some of these were being done by state programs. I believe there were watershed management programs that were bringing LiDAR into this, but the goal was we need elevation data that's better than the old USGS topo quads across the entirety of the state. Well, that was achieved. Most of it was achieved at just less than 1 point per meter. So if you think just looking down at the ground around your office chair, if you have 1 point per every chair, that's roughly what you were trying to achieve. It's a little less than that. And the accuracy was, for most of these projects, I believe, was about 0.61 feet vertical accuracy. It's good for a 2-foot contour. But technology's gotten better, software's gotten better, the sensors have gotten better, people have learned to use LiDAR data, so we need to collect this data again. There's a whole presentation on this, I believe, tomorrow. So the state has been working on having a new draft LiDAR plan to work with communities, federal agencies, utilizing this 3-step program. Again, this is a grant program where the federal and state and local agencies can work together to collect one set of data to meeting these certain specifications. So everything works together. The state wants to work within regions so that we're collecting data in a logical way. So if we're looking at the Minnesota River watershed, we want to collect that data as close to the same season as we can. And again, trying to bring in state funding, local funding to pair with the federal funding to try to make the cost less for every participating member. These are the general zones. You guys have seen these maps before. They've changed a little bit here and there. The big green area in the Northeast, for the most part, all of this data has been collected and actually is being processed right now. In the Southeast Driftless area, much of this area has been collected. Some of it's being processed now. The grants for the 2022 data collections were due October 1st. I think that was extended a week, but all of those have been submitted. So we'll see if the state wins another LiDAR grant. Also, the Red River area has contracted for additionally getting new LiDAR data. So long story short, you may be in a region that has brand new LiDAR or will potentially be getting brand new LiDAR data, and you can work with the state in order to try to bring that data to your county to take advantage of that grant program. The general spec. The general spec for the USGS 3-step program is what we'd call quality level 2. But what the state is looking to achieve through partnerships between the different state agencies, say DNR and DOT, and various agencies, They want to collect just one step better than that. So they're looking to do 8-point per meter LiDAR data across the entirety of the state. That's their goal. All of that data would meet a vertical accuracy of about 10 centimeter vertical accuracy RMSE-Z. So that's a root mean square error. How is that different from the last project? Again, we had 1 point per meter on the ground. Now we're looking to get to 8 points per meter on the ground. So 8 times the amount of data, for your surface. And it's actually about twice the accuracy. 10 centimeters roughly equals about 0.3 feet vertical accuracy versus 0.6. The other specifications on here are pretty basic. USGS requires for 100-foot streams to be given hydro break lines. So these would be looking at running water. If it's on average more than 100 feet wide, a break line should be collected on both sides of that river. And if you have ponded water that's greater than 2 acres, that should also have a break line going around the edge of that water body. The data is supposed to be classified so that you have bare earth as a classification. So if you were in an Esri environment, you could say, I just want to look at bare earth points, or I just want to look at water points. USGS also cares about bridge decks. And the other classifications that it cares about is high, medium, and low noise. That's what's in the base project for these grant programs. That's important to recognize. Some of you may have seen LiDAR data in the past that has buildings classified, trees classified. That's not in this basic USGS package. The grant process will include all the calibration points as well as independent vertical accuracy checks in both vegetated and non-vegetated areas. That's all spelled out in the LiDAR base specifications for what needs to be done for that. Now, the quality level 2, that really basic level, is 2 point per meter. So there may be opportunities for a quality level 2 project to still get grant funding. This is really common in several of the surrounding states, be it Wisconsin, Iowa, and others. Much of Illinois has all been done at QL2. It's the same accuracy standard, but it just has 2 points per square meter. And then there's something else called the quality level 0. They're still figuring out how to handle control on that for what that accuracy needs to be, but you can collect a higher density. Goodhue County is a great example of that. And there are other counties currently working on that where you have 30 points per meter. So what can you do with this data that you couldn't really do in the past? Well, you can map hydro much more accurately. You're looking at being able to map 20-foot streams or even 8-foot streams throughout an entire project area. If that's a watershed, if that's a county, if that's a municipality. As you're getting more and more points, you can create better and better building outlines. You don't have to trace it from imagery. You can utilize your LiDAR data. One great thing about LiDAR data is there's no horizontal shift. You're shooting a laser from a plane. It knows exactly where it is within that error ratio. So there's no 3-foot shift. There's no building lane or anything like that. The point is where the point is. In the same way, you can map tree canopy polygons. You can map much better contours. So a 0.3 vertical feet accuracy allows you to map 1-foot contours across an entire project area. With the resolution of the DEMs and the last data sets coming from this, you can accurately map your culvert inventory across an entire project area. We do a lot of that type of work these days. And obviously that culvert inventory is being used for hydro-enforced DEM, which gets used for water studies, soil studies, erosion studies. Slope analysis is really common to come out of this data. So that can be used for ordnance surveys and things like that. Erosion susceptibility mapping, zoning analysis, asset mapping. You can map your closed depressions. So those are areas where water is going to collect. It may not naturally sit, but it's going to collect there until it finally seeps through the ground. It has no natural exit. There's no culvert or river that's draining it. You can see some of the examples on the right where we've got change detection. You've got an urban tree canopy. You can see the building classification in the middle on the right-hand side here where the blue points are the buildings, and get an idea of why you can create a 2D building footprint from that data. And if you get higher accuracy data, you can even get 3D buildings. In the green image on the bottom here, you can kind of see what that hydro-enforced DEM would look like. So that allows water in a model to drain through the road because there's a culvert there, but a standard DEM wouldn't allow that to happen. So let's take a look at some of that data. 1-foot contours. Many of you are used to them. Data's gotten better and better. It's cleaner and cleaner. You can really get a great cartographic product out of the contours. I know many people that I work with. I work in an engineering firm. I still have engineers that ask me for contours when I actually have a last data set or a DEM. Always remember that contours are a derivative of a derivative. You're taking the last data set and you're creating the DEM, and then you're taking the DEM and creating the contours off of that. So really, if you can use it, use the last. If you can't use the last, use the DEM if you're doing surface projects. The contours are great cartographic representation, but they're really, really helpful in flat areas. You know, if you're on a big hill, you don't need to see the 1 feet, but when you get out to a flat area, you know, trying to understand that micro elevation change is really key. DEMs have gotten better. This DEM comes off of a QL2 project. You can clearly see that on the right-hand side of the image, we've got a road, it's got exits, it's got driveways. Just coming off of that, kind of the north side, you've got a gravel road. On the left side of this peninsula, you've got this 2-wheel drive track. This is obviously going to be a logging road or a 4-wheel drive road. And coming off of that, just going along the edge of the peninsula there, you've got what is actually a famous ski trail, the Birkebeiner Ski Trail in northern Wisconsin. This is Sawyer County, Wisconsin. This is entirely forested. So you're getting this type of resolution on the surface of the ground. And this is just with a QL2 project. So you can think about mapping your trails underneath the tree canopy. You can map unlogged forest roads, all sorts of types of information you can pull from data like this. This is a drumlin. You can even get into seeing details like glacial striation. So the glacier obviously came across, created this drumlin, this teardrop shape, and then you have a second time where the glacier pushed directly north to south across this drumlin, and you can see those glacial striations kind of on the north side of it cutting straight south. And you kind of see this jumbly thing near the bottom of the hill. That's that moraine where that glacier stopped on that second push. This image also shows you what you can do from a hydro standpoint. These would be 8-foot streams that can be clearly seen. If you've got a stereo environment, you can see this in your LiDAR data and map your hydro features to a very small degree across an entire project area. Case in point, the USGS spec, again, for mapping its break lines is a 100-foot stream. So we've got here is a fairly significant river. This yellow circle is about 100 feet. The yellow line in the middle of that stream right there, you can see that's about 30 feet. So that's exactly the type of stream that I put my canoe into, maybe pull out a fishing pole. It's a very important hydro feature to me, but it is nowhere close to meeting the spec to get documented within a USGS base LiDAR project. So thinking about mapping more granular water features is something that many, many counties and municipalities want to do with their data. Culverts. So this pink line, that's a culvert. We've all seen DEMs before. A road cutting across this wetland area that obviously has some drainage to it would typically be considered a digital dam in a water model. So you get a rain event, water's flowing from the north to the south. It's going to be coming through this wetland area. And if there's no culvert in the DEM, that DEM is just going to look like this 10-foot wall. So that water is going to pile up in the model up against this road. It's probably going to flow over to the south and over into this guy's side yard. That's obviously not reality outside of a catastrophic event. It's going to go through the road to this obvious retention area and continue to flow south through this wetland area. And again, you can see the same type of thing happening over on the image on the right. When we collect these culverts, we like to collect them ditch to ditch in order to try to make sure that the water is going to drain appropriately. Remembering that LiDAR data is a 3D environment, you can actually set the elevation of that culvert as well. When we're talking about how many culverts exist in projects, there's a lot. I meant a lot. This is one county. It's currently my record for an individual county. This one's just about 1,000 square mile county, and we collected nearly 34,000 culverts in one county. each one of them a 3D line that can be used for as a culvert inventory, but also used, in all the water modeling with that hydro-enforced DEM. We run a lot of different processes with software that's out there today. So you can start to find culverts and understand how a team like mine would be collecting that data. You can see the culverts right in the roads, just using a series of algorithms to try to better define where these locations are going to be. Once you get them all said and done, how do you get to 34,000 culverts? Well, we're able to collect normal culverts on a road, but you can also collect culverts for every single driveway. I was in northern Wisconsin in 2016 and 2018 when the floods came through. It wasn't just that you had lost US highways, just giant 40-foot holes in US highways, and all the county roads got washed out, but you also had everybody lost a driveway culvert, so people couldn't get into or out of their home. That's clearly an important emergency event. How can we replace these things so people can get in and out of their homes, get to a doctor, get to other safety, find other family? Their cars are stuck in their driveway or they just can't get home. So you can map a lot of culverts, and they don't have to be on roads. They can be off roadways. I had mentioned change detection. So this is another great thing for people in Minnesota. You have statewide LiDAR data. You're getting new statewide LiDAR data. So everybody will have the ability to go in and do comparative analysis. And the images on the right, we're talking about a very specific area. This actually speaks to the floods we're at, because we do a lot of mapping for the DOT. So in this case, we utilized the existing LiDAR and we scanned a new LiDAR data set. And we were able to accurately map where was the washout, how deep was it, and where did those materials go downstream? How is that going to affect water flowing into the future with all that material that's now changed the landscape downstream, but also how much clean fill needs to be brought back in order to try to reopen that road as quickly as possible. In an urban environment and just wide scale, you can see that we have, say in the south here, we've got a new Tractor Supply store. You're going to have building and zoning codes that are going to say we need to raise the footprint of that building up for drainage purposes. You may bring down the area around your parking lot, again, for drainage purposes. And then you're going to have retention and detention ponding. So you can see a couple buildings here that are new, and how did that work with parking and stormwater? That also looks to me, and I keep questioning, there must have been some guy selling in-ground pools or something around in a little community there, because they've got like 5 brand new pools or something that exist in people's backyards. Just the point clouds themselves and the software allows a new visual respect for what is going on in your community. This would be Goodhue County's project. So this is a 30 point per meter project. This is just outside of Red Wing, and on the back side of the bluff here is the new bridge going across the river. So that was the bluff that we're looking at here. So this is the original data that all of you have access to at the state right now. And when we redo this project, the amount of detail that comes out is truly significant. You can see hiking trails that were nearly invisible in the past. Obviously, we've got a new road, but just the level of detail. You can see boulders, you can see tree humps.
Hi, Adam, not to interrupt, I just want to make sure you're aware, 2 minutes left.
Okay. In an agriculture environment, we've got what looks like a washout. It's not a washout. We can see a tractors from the farmers driving across from one field to get to the next field. You can do soil erosion models. You can create slope models for building suitability or maybe manure spreading. And on the bottom side here, we've got that detention ponding I was talking about, areas where water is going to collect and has no natural outlet. You can map your trees. Again, soil erosion, trying to figure out where do we need to take into account what we're spreading, when we're spreading it, taking into account rain events, and what is going to be that total soil vulnerability. Doing that for entire watersheds or counties. You can do inundation modeling. So if you've got lakes that are growing, where's that going to go? That can be along a road or for a residential area. You can do flow accumulation models, trying to understand where is water collecting, where is it going, and how is it compounding throughout the entire drainage network. Very, very detailed in just a single field, trying to understand that you have 0.1 acres of drainage into some little tiny flow area in a rain event, and how that accumulates and where does that go downstream. How does that look with your slopes? How does that look like with your closed depressions? How accurate is that drainage? This is going to be a K farm, and we can see drainage accurately going across our paved surfaces within the K farm, going out its drainage area and into the spreaders. The water flowing just as we would expect it. Important to map, just in case it's not going the way you would expect it for an area that has high potential for pollutants. And you can map all of this data underneath the trees because the data is getting that good. I'm gonna jump over real quick, and I can try to answer questions as I show various data sets, but I know I'm coming up close to the end of my time. But realize that this LiDAR data is becoming more and more accessible. One of the first phone calls I took when I took my job at Ayres was I had a good friend at a county called me, and he had reached up onto his cadenza, found a hard drive, plugged the hard drive in, and realized, oh my gosh, I have LiDAR data. He had no idea. He's like, Adam, what do I do with this? Now you can start to load entire county LiDAR data sets and stream them online for free so that everybody can get access to the data. You can fly across, you can measure from the DEM in these 3D spaces. Sorry, my network bandwidth seems a little slow here.
So as we're waiting for the bandwidth to catch up, just to note, we need to start the next talk in 3 minutes. Adam, I invite you to talk a little more if you want to. You've got a really good attendance in the audience, but we do not have any questions yet. So if anybody has a question, please throw that in the Q&A now.
In a case like this, LeSueur County, one of the main reasons they're collecting new LiDAR data, and they were a partner with the state, they were looking to try to figure out where do we need to redigest the culverts across the entire project area. So they're doing a high density project, 30 point per meter project specifically for this because they're going to save on survey costs. So I can go into a tool like this, just the highway engineer using a right and left mouse button, and quickly measure from the center of my road to the center of a ditch. I've got 1.74 feet of elevation change, and they can zoom, through an entire county and understand what it is that they're dealing with the environment, save a ton of field time, and better design their projects with better answers. Again, just using LiDAR data. It was inaccessible data in the past.
Well, sorry, go ahead. If you can wrap it up in the next 30 seconds.
Yeah, sure. I know that there's counties that are going to be collecting higher density stuff, and I'm just hoping that my bandwidth continues to provide me something.
Oh, I'm going to interrupt you again. Adam, I have a question. I may have missed this, but where do we find this LiDAR data?
Well, the USGS will be pushing this stuff all through the .gov sites, but you can also, I believe the state of Minnesota is looking on how to host this data as they start to receive their 3DEP deliverables. Now, that said, the first 3DEP flights were flown in 2020. That was Goodhue County. That's a single county grant program. And there were several more counties flown in 2021. So that data will probably start to become available sometime in 2022. I am not the prime contractor for those projects, But the goal is going to be to make all that data accessible through the state. There may be somebody on the call that can answer that for sure, but you can certainly go to the session tomorrow on the LiDAR plan. They can answer that, but it will be eventually available through the .gov sites for the national map. So again, as you get denser and denser data, you can start to model a city in rapid fashion. This is the city of Milwaukee flowing with 30 point per meter LiDAR data. I believe this is going to exist in Le Sueur and Olmsted hopefully soon, and a few more counties coming up in the next grant cycle. Any other questions?
We are actually out of time at this point, Adam. Need to cut over to our next talk. Thank you so much for your talk, and always interesting to look at sort of the amazing visuals we can get out of LiDAR and what's happening on the web now as well. So thank you so much. Everyone else, please join me in thanking Adam virtually. And let's go ahead and switch into our next presentation. If you can stop your sharing, thank you again.
I'll be at my booth if you have more questions and can show more data. Feel free to stop by to the Ayres booth.
Great, thank you. And for our second talk in our LiDAR series this session, we're going to hear about LiDAR online data management and cataloging. And our speaker this time is Bob Vasquez from GIS Systems Developer with the City of St. Paul. And take it away, Bob. And feel free to share your video if you want to.
Oh, okay. I can turn it on. It's not a big deal.
Your preference.
Where I'm going with my presentation kind of dovetails with what Adam just showed you very well. He did kind of like the lead into how I got into LiDAR in the first place, and that was through the flight that was done in 2011 by the state of Minnesota. Basically, it's what kind of been rolling along on the shelves for a long time, and was available for a lot of uses, but it was kind of hard to use it, as Adam indicated, at least 10 years ago when it was made. It kind of sat on the shelf for us for quite a while before we really were able to utilize it very well. What I'm going to talk to you about is like, okay, everything that Adam said, I agree with everything he said there, but how do you manage this data? From a municipal perspective, we have a bunch of different needs than what somebody at like a county or a state might be worried about. So, you know, you've got different methods for collecting LiDAR as well. Adam kind of concentrated on, you know, the aerial angle of, you know, getting LiDAR, not exclusively, but that was kind of his general push there. But I'm going to kind of, you know, demonstrate that the LiDAR can be coming from different areas as well. So, you know, the point clouds can be generated in a number of different ways. You can actually take a series of photos that overlap each other and get a nice mat of overlapping photos and use that to generate a point cloud using photogrammetry, basically a bunch of math. Similar to the LiDAR lasers and, you know, that aspect of it, but I'm including them here for a reason, because these point clouds that come from drones, while they're not specifically or technically LiDAR, they have the same uses that in the end, you can build a 3D model out of that same data. So this particular one here is the Alliance Field out in Midway, St. Paul, and we had a contractor build this aerial drone data set for us to check the assets that are coming back with the stadium. So after the stadium is done, they pass all of the ownership back to all of the facilities and everything around the stadium. And that came back to us in this 3D model that was derived from the photography. Another method for collecting data is you can get the aerial LiDAR. This is what Adam was kind of pushing through. I'm actually showing the 2011 data set that was done by the state. So this is a chunk of that data. We clipped it out just for our uses at the City of St. Paul. And this is just another method for collecting LiDAR data points. And, you know, as you kind of zoom in on the data, you can see, Adam had indicated this as well, when you get certain resolutions, you start to see the sides of the buildings, but they don't always start to come out. But you can see that there's little gaps in what can be collected when you do an aerial collect from 5,000 feet up. But, you know, you're getting good representation of the building, you know, how high the roofs are and all those kinds of things. So you can see a lot of stuff just from that aerial data collect. There's also methods for doing mobile collect. You can also put a LiDAR on the back end of the vehicle and just drive down the street. What this does is it gets the LiDAR scanner really close to the stuff that you're trying to scan compared to, you know, an aerial collect. And the data comes in really densely. I mean, you're getting up in here into, you know, hundreds of points per square meter. It's almost like a solid is how dense the data is coming. And additionally, there's terrestrial LiDAR, or terrestrial LiDAR, which we use at the city. So we've got our own survey instrument, basically, that you can set out. And you set that out in a series around something that you're trying to scan. For this particular one, I think we had 12 sets of the instrument. So there's like, you know, 6 sets on either side of the bridge. And this just happens to be the first LiDAR set that we collected on our own with our new terrestrial scanner. And the data that you get back out of that is very, very dense. I mean, you can see here that the data is getting denser and denser as we move forward. And the resolution of it is very tight. This particular scanner also takes a photo every time it does its LiDAR scans. It takes a series of photos in 360 degrees, and it can use those to colorize the points that it scanned. So you get a very real-looking model in the end. Lastly, and more recently, you can actually scan LiDAR like from your phone. This is actually an app that you can run on your iPhone and on an iPad. And there's some versions of this for Android as well. But there's a big push by Apple to push out the idea that you can scan right from your phone. And you're able to just run around a particular item and just walk by it. And it'll scan with a LiDAR. There's actually a LiDAR sensor right in your phone. And these are the kinds of models that you can make with the particular LiDAR that's available in that phone. So you can see that the point I'm trying to make here is that, you know, while this is a sort of an emerging discipline, it's been around for quite a while, but the emerging discipline in my context is how do you manage the data? And these are the things that I'm worried about from municipalities' perspective is I may need to have this data accessible 20 years down the line, 30 years down the line. How do I organize this data? How do I put it away? It's a lot of data, you know, that kind of thing. So until very, very recently, there hasn't really been a comparable method for storing and accessing, you know, these multiple large point cloud data sets in an online manner. There's a couple of commercial avenues that you can take that are very, very expensive, and they take like a whole separate kind of knowledge base to be able to run them and administer them, you know, load the data, that kind of thing. There are a lot of products out and available right now that allow for a single individual model viewing and analysis. And managing the point cloud data, as I said, it's kind of a new and emerging discipline. And it's really hard to find any kind of information on the storage and being able to set this data for, you know, future use. The things that really got me into going down this route was trying to figure out how to manage the data and get it off the shelf and make it usable. From our perspective at the city, we're very interested in the engineering side of things. Bridge clearances, we have the culvert problems as well. There's we've actually done some big culvert scans that we had to do as well. So, but we're doing them very high resolution. These culverts I'm talking about were 20 foot by 20 foot. So, I mean, you could drive a car through them. That's how big they were. But you end up with very, very large data sets containing millions, billions of points. Historically, you know, you're kind of restricted in how much of a model that you could view at once, especially high resolution models. And you needed a pretty fast computer to be able to do anything with this kind of data. So, you know, the data tended to be kind of hard to work with. It's gotten a lot easier in the last few years. We're just getting started with it at the city. We've only been publishing in the form that I'm going to show you for about 2 years. We're already up to a terabyte of data, and we're just kind of scratching the surface. We haven't even really kind of got into this full strength yet. People are starting to come around and figure out how to use the data beyond just looking at a surface model. There's all kinds of things that you can do, as Adam indicated, in the previous presentation about doing measurements and stuff in the 3D models as well. But again, we're trying to save that data and make it accessible far out into the future. So in a proposed model of operations, I mean, this is kind of where I'm going with the presentation here. Is this is what we've done so far, the way we put things together. Coming at it from a municipal perspective, and it's built with an eye towards providing the data in an open format. That doesn't mean we're cutting out commercial access, but the data, there isn't really a good standard open format that everybody kind of agrees to yet for LiDAR. LAS has been around for quite a while, and everybody kind of reads that, but there's a lot of proprietary ones too that people are using as well, especially when you get into certain collection instruments. So some of that kind of stuff kind of muddies the water as far as the open data side of it. But it's kind of working out, and everything that we put together was with an eye towards making the data very convertible and in a very basic form or open form for reuse. Everything that's currently functional that we've got put together can be packaged for mobile operations too. So we can take all of what I'm going to show you out into the field if we needed to. That'll become important as we move forward here. So I'm going to show you what we do, the way we're doing things now, and then some little items about where I think we can do a little bit better, and then some future possibilities that I think will be of interest to the group. We've uploaded data that has been sitting on the shelf for years. When we had that first 2011 scan, I don't think we even touched it for the first 3 or 4 years. It just kind of sat on the shelf after we got the deliverable, because we didn't have any kind of method for managing the data or even chopping out pieces of it for our own use. We did put quite a bit of effort into increasing the resolution. When we got our deliverable for the 2011 data, we paid to upgrade the data to 8 points per square meter. So our data was a little denser than the rest of the state. But even though that was the case, we still didn't have a real good, easy way of using the data. Now we're able to mix and match different data sources and see them alongside of each other. This is our current published catalog. Not going to dwell on this, but the bottom line there shows that we've got 20 billion points in all of the data sets combined. So this is just basically a metadata output from one of our services. Getting into the architecture, what we put together, we're using an application that's called Poetry. It's an open source WebGL point cloud renderer for large point clouds. There are several comparable clients available, but we kind of zeroed in on Poetry. And then behind the scenes, we're using something called an Entwine database. It's a server-side 3D tile data storage service, and it also includes a programming API. So you can grab data by defining an area if you want to chop out or clip out a chunk of it and use it somewhere else. So this allows us to store the data at full resolution and retrieve it easily on the web at varying resolutions. We're currently putting together a prototype too for doing a 3D clip of chunks of points clouds for use in engineering apps like AutoCAD and Esri. Right now we're able to, this is a view of the 2011 LiDAR that I was talking about, and the Poetry interface. And then on the right side there is our published catalog. And if you'll notice here, it may be hard to see up on the top there, but there's this is running on an outside server called pwgeo.org. And you can get at all of this interface on your own as well on the outside. We were talking about the idea that you can see different LiDAR data sets together. The stuff on the left you're looking at is the 2011 data that was collected, and the stuff on the right is stuff that we collected about 2 years ago with our terrestrial LiDAR. And we're able to actually view these at the same time inside the same interface right alongside of each other. And what we've kind of come to the conclusion of is the 2011 LiDAR, because we put so much extra effort into doing the survey control on it when it was collected, we're able to use that as kind of like a truthing mechanism, so that as we take our and add our own terrestrial LiDAR into this database, we're able to see that we've got it collected correctly, it fits. The 2011 LiDAR is roughly about 2-inch accuracy. It's much better than that, but it's guaranteed to be 2-inch. And the stuff on the right is actually using survey control, and that's sub-centimeter accuracy. So we need to kind of close the loop on our circle of data, you know, the circle of life for our data streams and stuff. So by building these systems and automation tools for moving the data through into engineering and then back out for the construction piece is what's going to make all of this stuff reusable. We need to store and publish the data in open form where possible, and streamline post-production of the points. You know, when you pull the points into the office for doing your post-processing and stuff after the collection, that piece of it needs to be streamlined quite a bit yet. And then provide for alternate data formats. We've got some instances where we need, you know, we've got unique municipal needs. For example, all of the data that we're putting into our database, we've stored it in Ramsey County coordinates, because all of our records for going back for 100 and, well, almost 200 years now is all in Ramsey County coordinates. So AutoCAD is our primary target for the end use. It could be any number of commercially available apps, but AutoCAD's kind of our main tool. Our next level would probably be on the Esri side for the GIS folks. But you can get it at the data with the API with any web-based client. Just as an example here, you can see this is a chunk of a bridge that is basically a section through the bridge of the point cloud and pulled into AutoCAD. So you can see a section of the bridge deck. It's showing the bottom edges of the beams and then the railings right through the bridge deck. So why is all of this important? The same processes and data publishing services can be used for other visualizers, for example. So we can pull this data into AutoCAD and into, you know, Esri, or there's a bunch of other tools that are available as well online. And it can help with the development of the digital field side of things. So the collection tools and visualizers, you know, where does that all lead us to? The bigger deals that I'm seeing that are going to be coming down the line are in the augmented reality side of things. So you can see by this little video here that I've got up, what they did is they used that photogrammetry method, like the drone that I showed at the very beginning here. But instead of a drone, they're actually taking pictures. They took a series of pictures, probably even a video, just by walking along this open trench when it was open. And then what they've done is they've superimposed that out in the field with very high accuracy snapping. In other words, they're able to take the model that they collected earlier and snap it into the outside view that they're looking through, that, which is, you know, they're looking at through the camera on their device. So they can overlay those two things and then fade it in and out with the slider on the right there. So what this allows you to be able to do is collect that information when the trench is open and then superimpose it over the surface after the fact. So this is another example of the same kind of thing. These are just some videos that are available on YouTube and stuff, you know, that are along this this same kind of facility where you can see underground utilities and that kind of thing. I got another one here, and then once I get going through here, that you'll see how some of this stuff can flow together, though, for using them for like a one-call kind of strategy. If you needed to go out and dig something, and you have all of this stuff recorded. Basically, the idea here is you can just walk down the trench while it's exposed and build your own 3D model, and that becomes your record of inspection. And then the idea here is that you can superimpose that right out in the field as you're looking at it with your phone and see where everything is buried at. So we'll jump out to a demo now. And this is actually the poultry interface that I'm kind of leading up to here as I've been describing things. And what this shows here is this is actually a 3D model that you can view online on the web. And the Entwine database that I was speaking of allows you to manage the data in a very simple way for web use, in that it gradually will increase the points that it's displaying as you zoom in on a particular area. You can see as you're moving and zooming in on things, the data will automatically be downloaded in the higher resolution as needed. So what we're looking at here is the 2011 LiDAR data set. I mentioned already that we've got our catalog that is set up on the right side here. And we can also pull in other data. So I can pull in, for example, this Wabasha data set and zoom to that. And that's actually down here right in town. And if I turn off the LiDAR from the 2011, you can see there's the data that we're looking at. Now, because we're mixing and matching different data sets, you're using different classifications for the data points. So you have to make them appear in a bunch of different mechanisms and tools that are available here inside of poultry. So this is that Wabasha data set, and then I can turn the 2011 back on again, and you can see how that fits together. And this gives us our ground truthing as we're collecting these different data sets. So we know we're collecting the things correctly, and because they fit into the coordinate system when we're working with them. And then you've got tools inside of poultry here to do interesting things, like if I wanted a section, for example, through this area right here, the two buildings there, I can do that right inside of poultry and actually have it show the 2D interface. And there's the two building walls that it sees. And you have the option of scrolling in and zooming in and seeing that particular landscape there. And because the data is so dense, you're able to see quite a lot of detail, and we're only grabbing about a 7-foot swath of points. You can actually change this. So there's a depth of field there that's only 7 feet wide. I can go down to 3 feet, and the point number of points will go down a little bit that it's showing in the particular area here, but it doesn't really degrade it all that much. So you can see how useful some of this stuff is and how easy it is to use by the average kind of user online. So I'm going to restart it here and jump over into another area of the city.
As you're restarting that, just want to give you your 2-minute warning.
Alrighty. And I'm going to show you a little project that we did. This is Como Avenue, where the railroad bridge is over the top of it, up in northwest corner of the city of St. Paul. And then I'm going to bring up, let's see, where's the red line? This Highway 281, which was, these projects were actually done about a month and a half apart from each other. And it's very interesting that, they were so close to each other. You look at them from the top. Let's see, I gotta turn it around here. Let me turn off the attributes or annotations, I mean. That'll make life easier. So, you're looking at two different projects here, but you can see that because of their proximity to each other, there probably are value to be able to see the other project from the other one, in certain instances, and if you're trying to do certain things. And if you need a little bit more of a larger view, you can also pull in, something like the 2011 LiDAR and pull that in as well. You start to see where, the usefulness of some of this data starts to lend itself when you start being able to pull this information in such an easy way. And it runs pretty quickly. It's all dependent on the browser and the machine that the browser is running on. But the fact that you have the different methods in this interface to be able to turn things on and off and reduce the number of points that are being pulled in allows you to do a bunch of different things and be able to make this work. I mean, this particular interface will work on a phone as well. So, it lends itself to that AR perspective. So, any questions?
Yes. First, thank you, Bob, for that. We do have a few questions lined up. Let me start with one from Amanda Huber, who asks, what is the name of the database again?
It's called Entwine. You can just look it up. There's you can download how it works and everything. It's got its own website and everything.
I'm putting what I believe is the proper spelling in the chat.
W-I-N-E, yeah.
Yep.
That's probably
great. Thank you. And another question, did you consider using ArcGIS Enterprise for managing the data? AGO and Enterprise can serve open source and REST services for more native capability with CAD and Esri apps if that's what you're after.
Right up until the price tag came out. That's my answer.
Were there other considerations?
Well, the bigger deal right now is our main customer base is AutoCAD based, and we really need to be able to get that data into the AutoCAD users' hands. We don't have a good, how do I say this? We don't have our administration of our Esri services set up adequately to be able to manage something like this, because this is a whole nother kind of theater of operations beyond GIS, straight GIS, getting into the 3D side of things. Our engineering is just starting to get into the, feel the notion of why is 3D important. I mean, we're just starting to move away from, going the 2D route. I don't doubt that we'll probably get there at some point.
Thank you. Another question, this one from Luke Henderson. Can you share the link to some resources for the mobile app that showed the open trench?
I can't remember. You know what, I'm gonna have to get back to you on it. I probably should have put a little sheet together on that. Oh, wait, I might have it here. Go on to the next question while I look here.
Let's see. Another question. I actually caught the PWGO link in your chat. Is it okay if I'm sorry, in your talk? Is it okay if I put that into the chat? The pwgo.org/apps/ well, I'm saying it, so maybe I should just put it in.
Yeah, put it in that way. The poetry. Yep.
Okay. Didn't want to overload your server or somebody's server if 40 people hit it at once. Okay.
Well, that just lets me beg for more money to.
New hardware, more hardware.
Yep, you got to leverage what you can where you can.
And we are temporarily out of questions. If anybody else has anything, please feel free to throw it in the Q&A section.
I'm putting some links into the chat that they can go and grab some of that information about the. Actually, from another presentation I got to do. So fortunately, it was easy to find.
Fantastic.
There you go.
Great. I will make sure we're up for at least another minute. You still have about 2 minutes, Bob. If there are other questions, happy to entertain them. I will say I appreciated your reference to LiDAR rather than LiDAR. Haven't heard that in a little while, so nice to hear it occasionally. There were two.
I think I've been playing around with this stuff way too long.
Let's see. Well, if there are no other questions, let's go ahead and thank Bob for another great talk. And again, as with the previous one, always great to see interesting and amazing to see what's going on with the LiDAR data out there, how to manage it, and what you can do with it on the web, among other things. So thank you very much, Bob. Let's give him a virtual round of applause. I do, in the last minute, if it's okay, Bob, want to put into the chat a couple of things, since there's been some LiDAR discussion going on here, obviously, and at the rest of the conference. There are 3 more sessions. The Minnesota LiDAR Plan panel, which Sean Vaughn, who's one of the panelists, mentioned a little earlier in the chat. That's tomorrow from 11 to 12:30. Then at 1:30 to 3 tomorrow, there's the county level LiDAR project panel. I believe that was Goodhue County, if memory serves. And on Friday, there's the LiDAR for Minnesota Forest Inventory panel from 10 to 11:30. So if you came to the conference for LiDAR, you are well set. And the clarifying point from Sean Vaughn a little earlier, there was a reference earlier to the state as the leader for the current LiDAR initiative, and just clarifying that, and again, this is in the chat, it's actually being led by the 3D Geomatics Committee, which is a chartered committee under the Geospatial Advisory Council. And that is the group that is going to be doing the Minnesota State LiDAR Plan panel tomorrow. Well, seeing no other questions for Bob, Bob, thank you again, and Adam as well, and thank you to all the attendees. Hope you're having a great conference, and see you in the vendor hall or elsewhere. Thank you, and have a great afternoon.